What if I informed you that at this moment, Neptune is carrying the scars from a collision so enormous it unleashed the energy equal to millions of nuclear bombs? The James Webb Space Telescope has recently captured something that ought not to be feasible. A massive object potentially hundreds of kilometers wide crashing into the outermost giant planet in our solar system. This is not science fiction. This is occurring right now. And the proof is irrefutable. The shock waves continue to ripple through Neptune's atmosphere, forming atmospheric scars that have never been observed before on any planet within our solar system. In the immense quiet of space, Neptune has consistently been among the least comprehended planets in our solar system. It resides so distant from the Sun that even our strongest telescopes based on Earth have difficulty capturing anything beyond faint blue contours of its storms and misty atmosphere. For many years, Neptune remained merely a remote giant, enigmatic and frigid, with just sporadic views offered by Voyager 2 during its 1989 flyby. Since that time, our understanding of the planet had altered very little, until this point when the James Webb Space Telescope directed its attention toward Neptune. Researchers anticipated refining the knowledge we already possessed. Its stormy weather patterns, atmosphere rich in methane, and subtle icy rings. But rather than standard information, Webb documented something genuinely astonishing. Its potent infrared vision uncovered irregularities that failed to match Neptune's typical atmospheric profile. Webb identified an abrupt surge of thermal radiation, clear indicators of heat bursting through Neptune's clouds. In addition to this, light fluctuations spread across the upper atmosphere, emerging and vanishing as if the planet had been hit by some unseen power. These indicators were not arbitrary interference. They were steady, potent, and much too peculiar to ignore. Astronomers instantly recognized that something remarkable had taken place. The information indicated a huge release of energy, one inexplicable by regular weather phenomena, thermal and shockwave evidence, or heating from the sun. Instead, the signs directed toward a fierce external origin. And while investigators examined Webb's infrared data frame by frame, an astounding deduction started to form. Neptune had probably undergone a massive collision with an enormous object. This was no minor strike, like a meteor streaking through Earth's sky. The markers implied something considerably bigger, a body large enough to unsettle Neptune's whole atmosphere. The shock waves documented by Webb suggested an impact of proportions that could reshape a planet, the type of collision capable of imposing enduring scars on the gas giant. For the scientists monitoring the data as it developed in real time, it represented a pivotal moment. Neptune, a world so far away that sunlight requires over 4 hours to arrive there, was abruptly disclosing one of the most intense events in contemporary planetary history. And due to the James Webb Space Telescope, humanity possessed a prime view to observe it. The initial hint of Neptune's collision appeared as heat, intense, unnatural heat. Typically, Neptune ranks as one of the chilliest planets in the solar system, with average temperatures dropping below -200 degrees C. Its atmosphere, ruled by hydrogen, helium, and methane, retains minimal warmth from the sun. But when James Webb examined the planet, its detectors disclosed something no astronomer anticipated encountering: a sudden and forceful increase in thermal radiation, erupting from the upper strata of Neptune's clouds. This energy spike could not be accounted for by the planet's usual weather cycles. Neptune's storms, although fierce, are powered by internal heat and sunlight taken in by the atmosphere. However, the data from Webb displayed something distinct: an immense infusion of energy, as though a foreign entity had collided with the atmosphere and discharged inconceivable quantities of heat instantly. Before we proceed further, press that subscribe button and activate notifications. You won't want to overlook any updates on the universe's profoundest secrets. And if you enjoy delving into concealed mysteries and unexplained findings, like this video, so we recognize to continue revealing them. Even more astounding was what came next. Webb's infrared sensors documented rippling shock waves expanding outward across Neptune's gaseous strata. Picture hurling a huge stone into a calm lake. The ripples spread in all directions. Now, substitute the lake with Neptune's atmosphere and the stone with a cosmic trespasser, and you start to grasp the magnitude of what Webb observed. These shock waves did not go unobserved. They produced evident distortions in the planet's framework, interrupting jet streams and altering cloud formations. For the first time, astronomers could observe visible scars inscribed into Neptune's weather system. Vast bands of clouds extended and contorted in unnatural manners. Neptune's unique atmospheric response, tracing the root of the disruption. It was as if Neptune had been bruised by the immense force of the impact. The occurrence was without precedent. On Earth, shock waves from major impacts can fracture rock, initiate tsunamis, and modify climate for years. On Neptune, a world lacking a solid surface, the outcome was even more striking. The impact energy disseminated through the dense atmosphere, scattering heat and turbulence across a planet 4 times Earth's diameter. Webb's tools recorded everything in exquisite detail, providing scientists with the initial glimpse ever of how an ice giant responds when hit by a massive intruder. What renders this discovery even more significant is the infrequency of such events. Collisions on this scale are not routine happenings for Webb to document one so vividly, and in real time implies we are observing a cosmic incident that might occur only once in thousands, or perhaps even millions of years. It was as though Neptune, typically a remote and silent giant, abruptly cried out across the solar system. Something remarkable has occurred here. Once the proof of heat and shock waves was verified, the inquiry became inevitable. What precisely struck Neptune? To unleash such a vast amount of energy, the colliding entity had to be much more than a mere fragment of rock or ice. It was not a meteor, the sort that burns innocuously in Earth's skies. This was something far grander, far more potent. Through meticulous analysis of the thermal radiation and the propagation of shock waves, scientists started estimating the object's size. Their deduction was breathtaking. The impactor was probably tens, possibly even hundreds, of kilometers across. To provide perspective, an object merely 10 kilometers wide is thought to have eradicated the dinosaurs on Earth 66 million years ago. The body that hit Neptune could have been 10 times larger, bearing energy on a scale nearly beyond comprehension. But where might such a giant have originated? Astronomers directed their focus to the Kuiper Belt, a broad area of icy remnants and dwarf planets circling beyond Neptune. This is the identical region where Pluto exists, along with innumerable frozen bodies remaining from the solar system's formation. Occasionally, gravitational pushes from Neptune can displace one of these icy nomads, propelling it inward on a fatal path. Another option is that the intruder was a rogue comet, a body adrift in the solar system, roaming for millions of years until it intersected Neptune's trajectory. With Neptune's tremendous gravity, 17 times Earth's, it would have been nearly impossible for such a voyager to evade capture once nearby. Instead, it would have been pulled inward, speeding up to astonishing velocities before crashing into the planet's thick atmosphere. Events' impact on Neptune's extreme weather and exoplanet lessons like this are not only fierce, they are also extraordinarily uncommon. In the current solar system, collisions of this extent are believed to occur on timelines of millions of years. To truly observe one, and with such sophisticated tools as the James Webb Space Telescope, is a stroke of cosmic fortune of the utmost degree. What makes this even more extraordinary is that Neptune may now function as a natural repository of the collision. Fragments from the impactor could stay suspended in its atmosphere, identifiable as odd chemical markers. For scientists, this signifies Neptune is not merely a planet, but a time capsule containing material from the solar system's outer fringes, or perhaps even from farther. In one event, Webb permitted us to glance back in time and view the turbulent processes that once formed every world we recognize. For Neptune, this collision might be one segment in a narrative of recurring cosmic meetings. And for us, it serves as a striking reminder that even in the apparently stable solar system of today, the reverberations of creation are still being inscribed in fire and ice. On Earth, an impact deposits a scar of stone and ash. On Mars, craters and dust storms bear witness to fierce collisions from ancient times. But Neptune is distinct, profoundly distinct. This far-off giant lacks a solid crust for an object to crash into, no bedrock to seize the mark of ruin. Instead, Neptune is a realm of pure atmosphere, a planet composed almost wholly of swirling hydrogen, helium, and methane gases. And thus, when the intruder hit, the result was unlike anything we have ever seen on another planet. The massive body did not etch a crater or disperse boulders across a desolate plain. Instead, it was engulfed alive, drawn into Neptune's deep gaseous strata, where the crushing density of the atmosphere ripped it apart. Piece by piece, the impactor disintegrated until its enormous energy, built up over billions of years of journey through space, was liberated in a single catastrophic instant. The pure ferocity of that liberation is hard to fathom. Astronomers calculate that the impact released energy, equivalent to millions of nuclear bombs, detonating simultaneously. Envision the combined ruinous power of all weapons humanity has ever made, multiplied many times, erupting in one moment. And even then, you would only be touching the edge of the force involved. What ensued was not a lone explosion, but a sequence of reactions echoing throughout the whole planet. The heat surge rushed upward, sparking violent chemical reactions in Neptune's upper atmosphere. Layers of methane and hydrogen were torn asunder and recombined, creating clouds of peculiar new compounds, molecules that had never appeared there before. For the first time, astronomers could directly witness the chemistry of an impact on an ice giant, unveiled through the James Webb Telescope's sensitive infrared vision. Unlike a rocky world, Neptune could not maintain a permanent crater as a recollection of what transpired. Instead, the proof was inscribed into its weather. Webb sees the aftermath. Vast atmospheric scars swirling with turbulence extending thousands of kilometers across. Clouds stable for years were fragmented and scattered. Familiar storm systems distorted out of form, and new ones emerged, seemingly in an instant. Astronomers even detected shifts in Neptune's signature dark spots, implying that the impact had remolded the very flow of the planet's winds. The scars were not just apparent, but persistent. Pockets of extreme heat kept radiating from the entry site long after the object had dissolved. Massive turbulence ripples echoed outward, disrupting jet streams that encircled the planet at incredible speeds. In certain areas, the haze at high altitudes grew darker, producing unusual shadows and color shifts that had never been noted before. Neptune, typically tranquil in its cold blue tones, now seemed bruised, its atmosphere imprinted by the hand of violence. For scientists, this was an epiphany. They had long speculated what a giant impact on a gas or ice giant might resemble, but no one had ever viewed it so distinctly. Here was evidence that Neptune could be scarred, not in stone, but in air, chemistry, and movement. The planet itself had taken in the impact, reshaping its atmosphere in ways that may require decades or even centuries to stabilize. On Earth, such a collision would have terminated life as we know it. On Neptune, it transformed into something entirely different, a cosmic experiment on a planetary level, a glimpse into how the solar system's most enigmatic worlds develop under the force of violence. And thanks to the James Webb Space Telescope, humanity now possesses the first clear documentation of such a rare and extraordinary occurrence. In the silent obscurity beyond Neptune, the James Webb Space Telescope did more than merely capture a burst of heat. Its powerful infrared spectrometers enabled scientists to look directly into the chemical turmoil left by the collision. What they discovered was astounding. Webb showed that the impactor had not simply disappeared into Neptune's vast blue atmosphere. Instead, it had infused the skies with new molecules and elements, foreign substances that had journeyed across the solar system and now merged with the chemistry of the ice giant. This was the instant when Neptune, for the first time in documented history, was imprinted by the fingerprints of a visitor from the Kuiper Belt. Among the most notable findings were unusual markers of ammonia and carbon dioxide, compounds not typically present in substantial amounts in Neptune's upper atmosphere. There were also faint but unmistakable alterations in methane, a gas that usually controls Neptune's chemistry. These changes suggested fierce reactions ignited by the immense heat of the collision, reorganizing Neptune's atmospheric composition in mere seconds. But the surprises continued beyond that. Webb's instruments also indicated the presence of exotic ices and hydrocarbons, the sort of fragile compounds thought to exist in the frozen depths of the Kuiper Belt. These are materials created in the coldest expanses of space, where sunlight is faint and temperatures drop to near absolute zero. For scientists, it was akin to receiving a sample of the outer solar system's chemistry delivered straight into Neptune's skies by a cosmic envoy. This discovery was more than a novelty. It was a breakthrough. Each detected molecule functioned like a clue to the impactor's source. Was it a piece of a Kuiper Belt dwarf planet, a rogue comet on a prolonged wandering orbit, or perhaps even a survivor from the early solar system, a remnant from the chaotic era when the planets were still taking shape? By examining the chemical fingerprints remaining, scientists could start to rebuild the tale of where this object originated and what it consisted of. The chemical disorder also revealed something about Neptune itself. When the impactor dissolved into the atmosphere, it dove deep, agitating layers of gas that seldom interact with the upper skies. In the process, it brought up concealed materials from Neptune's interior, compounds usually secured beneath crushing pressure. Webb spotted hints of these too, implying that the impact had briefly opened a window into the hidden chemistry of Neptune's deeper strata. For planetary scientists, this was exceptional. They were not simply investigating a collision. They were effectively conducting a cosmic laboratory experiment, one impossible to replicate on Earth. A Kuiper Belt body, untouched for billions of years, had been shattered open. Its chemistry poured across Neptune's clouds, then analyzed by Webb from 1,000,000 miles distant. These fingerprints may diminish over time, scattered by Neptune's fierce winds, but for the present, they persist as a record of both the impactor's identity and Neptune's concealed depths. Every molecule narrates a story of icy beginnings, of violent change, and of a planet still being molded by the solar system's forces. And in that regard, Neptune's skies have become more than mere clouds of gas. They are a canvas of chemistry, illustrated by the hand of a collision that journeyed millions of miles, only to conclude in a firestorm that Webb captured in exquisite detail. Neptune is already a realm defined by extremes. Even prior to the collision, it was recognized for its swiftest winds in the solar system, roaring at speeds exceeding 1/500 nm/s. Storms larger than Earth swirl across its cobalt blue atmosphere, and the planet's dynamic cloud systems continually change, forming dark spots and bright bands that emerge and disappear over months. It is a planet in perpetual motion, a living lab of turbulence. But when the massive impactor struck, it basically shifted the equilibrium of Neptune's already fierce atmosphere. The energy liberated by the collision was not limited to one spot. It disseminated across the planet, infusing heat and momentum into the wind systems like an invisible force hastening the storm. Abruptly, the familiar configurations of Neptune's weather were interrupted, spawning new storms much stronger than any seen before. Webb's infrared and visible light tools unveiled the aftermath in stunning detail. Bright new spots materialized across the planet, regions of intense heat and activity that had been absent previously. Long, elongated clouds extended across thousands of kilometers, formed by winds supercharged by the impact. Even Neptune's signature dark spots appeared to adjust in response, as if the planet was adapting to the unleashed energy. The collision also generated massive vortices, spinning storms of a scale and intensity without precedent on Neptune. Some of these storms rotated so quickly that they could produce wind speeds matching or even exceeding the planet's usual peaks. Webb identified swirling turbulence, chaotic cloud patterns in decading the atmosphere was still attempting to steady itself months after the impact. Scientists conjecture that these storms may endure for years, slowly dispersing the collision's energy while imposing a permanent mark on the planet's weather system. The implications are deep. Neptune is a planet whose actions are mostly concealed from observations on Earth. And yet this solitary impact provided astronomers a rare chance to observe how an ice giant reacts to a sudden energy influx. By examining these supercharged storms, researchers can learn not only about Neptune itself, but also about the physics ruling gas and ice giants throughout the galaxy. In effect, the impact converted Neptune into a planetary-scale experiment in extreme meteorology. The energy, momentum, and chemical aftermath all merged to form a dynamic system unlike any observed before. Webb's instruments seized it all. The bright spots indicating bursts of heat, the elongated clouds extended by furious winds, and the swirling turbulence suggesting storms far larger than any previously documented. For scientists and the rest of us observing from millions of miles distant, the lesson is evident. Neptune is not merely a remote cold giant. It is a living, breathing world capable of dramatic transformation, whose extreme weather can be amplified by events that propagate through the outer solar system. And thanks to the James Webb Space Telescope, humanity now possesses the first ever prime seat to observe this cosmic drama develop. The collision on Neptune was not a solitary incident. While the planet absorbed the majority of the impact, the surrounding system, its 14 moons and delicate ring network, could not stay unaffected. These moons, varying from tiny, irregularly shaped rocks to the massive and mysterious Triton, are linked by Neptune's gravity in a delicate celestial ballet. The impact released a flood of energy and debris, a fierce disturbance that may have echoed throughout the system. Webb's sensitive tools suggest that dust, ice particles, and fragments from the impactor may have been propelled far beyond the upper atmosphere, drifting outward into the ring plane. Neptune's rings are faint and wispy in comparison to Saturn's, but even minor alterations can be spotted. Scientists hypothesize that this material influx could have temporarily densified certain sections, brightened faint arcs, or produced transient streaks visible in the infrared spectrum. Each debris fragment serves as a cosmic fingerprint, a direct record of the colossal impact and the chaotic forces it released. Meanwhile, the moons themselves may have undergone both physical and chemical alterations. Smaller moons, continually pelted by micrometeorites, may have acquired a fresh layer of material from the collision, slightly changing their surfaces. Triton, Neptune's largest and most enigmatic moon, could have been especially influenced. Its icy surface and tenuous atmosphere might have reacted with fallout from the impact, igniting chemical reactions in the ice and perhaps even temporarily modifying its thin nitrogen atmosphere. The collision's energy may have also caused minor gravitational disturbances, subtly shifting the orbits of moons and sending ripples through the system. The interconnectedness of Neptune and its satellites emphasizes a remarkable truth. In a planetary system, nothing exists separately. A single extraordinary event on the planet can cascade outward, impacting rings, moons, and even the dynamics of the surrounding space environment. By observing these changes, astronomers gain a rare opportunity to study planetary system evolution in real time, an invaluable perspective on how energy spreads through a complex, interrelated system of gas, ice, and rock. Moreover, the potential long-term consequences are profound. Rings that are temporarily brightened or thickened may gradually return to their original setup, but subtle changes in moon surfaces or orbits could last for decades or even centuries. Over time, the system may seem slightly different to future observers, a permanent record of a single violent encounter that happened millions of miles from Earth. This impact reminds us that Neptune is far more than a distant cold blue world. It is alive with motion, chemistry, and gravitational complexity, a giant that responds dynamically to external forces. Every moon, every icy ringlet, every cloud in its atmosphere reacts to the unleashed energy. Webb has provided humanity with a prime seat to witness this cosmic interplay, capturing a rare moment when a distant ice giant, its moons, and its rings were collectively remodeled by a single cataclysmic event. In essence, the collision acts as a vivid reminder that the solar system is a living, dynamic environment where even worlds at the very edge are constantly evolving, reacting, and transforming. Neptune, once viewed as a quiet sentinel in the outer reaches of our solar system, has revealed itself to be a planet of dramatic consequences. A system where every impact, no matter how distant, leaves a lasting impression on the entire celestial neighborhood. Collisions are not just random mishaps in the cosmos. They are one of the most fundamental forces that mold the evolution of planets. From the early chaotic days of the solar system to the present, impacts have played a crucial role in determining planetary atmospheres, surface chemistry, rotation, and even the formation of moons. Each collision transports energy, material, and sometimes life-altering ingredients across the vastness of space. Neptune, with its thick, gaseous layers and extreme environment, is no exception. While it may appear distant and cold, it is an active world continually reshaped by external forces. A single massive impact like the one captured by Webb has multiple profound effects. First, such collisions can deliver essential volatiles, including water, ammonia, methane, and organic molecules carried from distant regions like the Kuiper Belt. These ingredients may seem minor, but over time they add to the chemical complexity of the planet's atmosphere. The impact also modifies magnetic fields and rotation dynamics. As energy is transferred through Neptune's interior, subtle changes in rotation or shifts in the planet's magnetosphere can happen, influencing how charged particles travel through its upper atmosphere and affecting long-term climate and storm patterns. Even the planet's atmospheric circulation, from winds to storm intensity, is remolded, leaving enduring signatures of energy and turbulence. Beyond Neptune itself, this event offers a living illustration of how planets continue to evolve long after their initial formation. Unlike the early solar system when collisions were frequent and catastrophic, today's impacts are rare. But when they occur, their effects ripple across planetary atmospheres, moons, and rings, reminding us that no planet is static. Each collision is a cosmic experiment, demonstrating how energy, momentum, and material are redistributed throughout a planetary system. Studying such impacts enables astronomers to draw parallels with exoplanets far beyond our solar system. Understanding how Neptune reacts to a single collision helps us predict how similar ice giants, common throughout the galaxy, might behave under extreme conditions. Webb's observations are not just about one moment in time. They are a window into the life cycles of planets, showing that even giants at the edges of their systems remain active, dynamic, and constantly evolving. In essence, this collision is a reminder that planetary evolution is ongoing. Planets are not frozen relics of the past. They are living, breathing systems shaped by interactions, both violent and subtle. Each impact, whether massive or minor, leaves a trace, gradually sculpting worlds and ensuring that the cosmos remains a theater of constant change. The collision on Neptune provides more than just insight into our own solar system. It offers a unique window into the lives of distant worlds. Over the past 2 decades, astronomers have found thousands of exoplanets orbiting other stars, many classified as hot Neptunes or mini-Neptunes. These planets, often similar in size and composition to Neptune, but much closer to their stars, exhibit atmospheres and chemical signatures that are sometimes puzzling. By observing a real-time impact in Neptune's atmosphere, scientists now have a baseline for interpreting sudden anomalies on distant exoplanets. For instance, if an exoplanet's atmosphere unexpectedly brightens or displays new chemical compounds, astronomers can compare these signatures with Webb's observations of Neptune to ascertain if a recent collision might be responsible. This is revolutionary because it turns speculative theories about exoplanetary impacts into data-driven science. The specific molecules Webb detected on Neptune, ammonia, methane variations, exotic ices, and other volatiles serve as reference points for interpreting exoplanet spectra. Previously, unusual chemical readings could be wrongly attributed to exotic atmospheric processes. But now, scientists can determine whether these anomalies are the fingerprints of collisions with large bodies like Kuiper Belt objects or rogue comets. Moreover, the Neptune impact provides clues about planetary system evolution beyond our solar system. In tightly packed exoplanet systems where gravitational interactions are more intense, collisions may be more frequent. Understanding how Neptune responds to a massive impact, how its atmosphere absorbs energy, how rings and moons are disturbed, and how chemical fingerprints are distributed allows astronomers to predict the consequences of similar events on exoplanets, even when those worlds are hundreds of light years away. This event also highlights the importance of long-term monitoring of exoplanet atmospheres. Just as Webb caught a rare moment on Neptune, future telescopes can detect transient events on distant planets. By building a catalog of collisional signatures, scientists can reconstruct the history of planetary bombardment in other systems, offering insights into how planets gain or lose atmosphere, how moons form or are altered, and how planetary climates evolve under extreme conditions. Ultimately, Neptune's collision is a reminder that planetary evolution is universal. What we witness in our own solar system provides a laboratory for understanding worlds far beyond it. Each giant impact teaches us about the dynamic nature of planets, the role of rare but transformative events, and the intricate interplay of chemistry, physics, and gravity that shapes every celestial body. Webb has given humanity a front-row seat, not only to Neptune's drama, but also to the cosmic processes that likely unfold across billions of other planetary systems. By studying this single event, scientists can now connect the dots between local observations and distant exoplanet mysteries, turning what was once theoretical into concrete, observable science. It's a vivid reminder that in a universe filled with planets, moons, and wandering icy bodies, chaos and collision are essential to the story of planetary life. Whether near or light years away, the Neptune impact has revealed a side of the James Webb Space Telescope that few had fully appreciated. While it was designed to peer into the furthest reaches of the universe, capturing light from the earliest galaxies and unraveling the story of cosmic evolution, Webb has also proven to be a remarkably capable sentinel within our own solar system. This discovery showcases the telescope's ability to operate not just as a window to the past, but as a real-time observer of dynamic high-energy events happening right in our cosmic backyard. By detecting the thermal bursts, atmospheric disturbances, and chemical fingerprints of a massive impact on Neptune, Webb demonstrated an unprecedented level of precision and sensitivity. It could detect subtle changes in light and heat, track the spread of shock waves across an entire planet, and measure the introduction of exotic molecules into the atmosphere. This is a capability that was once thought impossible for a telescope primarily designed for distant galaxies, showing that Webb can function simultaneously as both deep space explorer and planetary monitor. The implications for science are enormous. Humanity now has a tool capable of observing rare transformative events in the solar system, events that may occur only once in decades or centuries. Collisions like the one on Neptune, comet flybys, or even sudden storms on gas giants can be monitored with precision, giving scientists the chance to study planetary evolution as it happens rather than reconstructed from historical data or models. Webb's ability to detect these occurrences opens a new chapter in solar system science, bridging the gap between planetary astronomy and cosmology. Beyond our solar system, this capability has ripple effects for exoplanet research. Webb's sensitivity to atmospheric changes and chemical signatures allows scientists to draw parallels between local events and distant planets, helping them identify potential collisions or sudden atmospheric phenomena on worlds orbiting other stars. In essence, the telescope can act as a cosmic detective, piecing together the lives of planets both near and far by observing the subtle fingerprints of high-energy interactions. Perhaps most importantly, Webb's observations highlight a profound shift in how we understand humanity's place in the universe. For the first time, we can witness the dynamism of planets in real time, experiencing cosmic events as they unfold millions of miles away. We are no longer limited to static snapshots of distant worlds. Instead, we can monitor their ongoing evolution, chemical transformations, and the dramatic consequences of rare events that shape planetary systems. This dual role as a window to the early universe and as a guardian of our solar system cements the James Webb Space Telescope's legacy as one of the most versatile and groundbreaking instruments in human history. Its discoveries remind us that space is not static. Whether it's a galaxy forming billions of years ago or an ice giant like Neptune being reshaped by a massive impact today, the universe is alive with motion, energy, and change. In the end, Webb has not only expanded our knowledge of distant galaxies, stars, and exoplanets, it has also broadened our awareness of the immediate dynamic cosmos around us. From the violent collision on Neptune to the storms that rage on distant worlds, Webb stands ready to capture the universe's most dramatic moments, proving that the cosmos is far more active, connected, and fascinating than we ever imagined. Humanity now has a telescope capable of tracking the universe's most extraordinary events, turning science fiction into science fact and giving us a front row seat to the ongoing drama of our solar system and beyond. With Webb watching, we are not just observers of history. We are witnesses to the universe's living, evolving story. From Neptune's sudden violent collision to the lessons it teaches us about distant exoplanets, this discovery reminds us that the universe is alive, dynamic, and full of surprises. The James Webb Space Telescope has shown us that we no longer need to rely solely on theories or static images. We can watch cosmic events unfold in real time, capturing moments that were once beyond human reach. Every impact, every storm, and every chemical fingerprint is a story waiting to be told. And Webb gives humanity the ability to read it. We are witnessing not just the evolution of a planet, but a broader narrative about how planets, moons, and entire systems continue to change even billions of years after their formation. As we look to the skies, we realize that the cosmos is not a distant, unchanging stage. It is a living theater where collisions, storms, and explosions continually shape worlds. And now, with Webb as our eye in the sky, humanity has a front row seat to the greatest show in existence. So as we marvel at Neptune, remember the universe is full of wonders still waiting to be discovered. And every new observation brings us closer to understanding our place among the stars. If this journey through Neptune and beyond fascinated you, subscribe to our channel to witness more cosmic mysteries and leave a comment sharing which planetary discovery excites you the most. The universe is unfolding, and we're here to explore it together.